Okay, excuse me. Let's start the afternoon session. This is the picture that taken in March 1998, showing 3 generations of Fano's family: a middle-aged son, teenager son, and teenager grandson. The key point of this picture is Hugo has been looked that way for the 30 years I have known him. Because Hugo always like to do time-independent picture, and that's how you get. You stay the same. Fano profile doesn't change with time. For those of us who have some experience working with Hugo, most of you have some story to tell, and this is the well-known story. What's new? However, of course, Fano has all kind of philosophical remark on many things. The one which I have, I think, impact me the most actually is this sentence. It's not even wrong. So here we go to this discussion of the paper, and say this paper is not even wrong. So the assumption could be worse than it not being right. Of course, the point is, I think, is that his message is you should do the problem, pick up the right problem and do the problem the right way. So in Hugo's way, you not just do physics, but he also teach you how to do physics. And the way I understand is, the way he sees things is you start with some experimental data, and your goal is not just to make some calculation as a theorist, to do some calculation to match the experimental data. The data is to encourage you to generate some concept or provide some pictures or even some new language so you can generalize this language or picture to broader aspect of physical world. After you have picture and language, you can do theory, can do the computation, and then you can go from there to either compare experiment or propose some new experiment. Of course, we always talk about talking about pictures. Picture means we have to have something to be visible in front of us, and of course, a lot of people as a theorist do a lot of calculation of wave function. But frankly, how many wave functions have seen? Most wave functions have seen actually is hydrogenic wave functions, because the typical wave function is multidimensional space. And of course, everybody talk about the story that Hugo talk about this double excited state of helium. Once he has seen the data that you can no longer use the shell model to explain the double excited state. Now, of course, if you just look at experimental data, immediately after experiment on double excited state, already there's many calculations, cross-coupling or configuration interaction type approach, predict all the experimental spectra. To many people, that's enough. The experiment is already explained. But for Hugo, that is something more fundamental, saying, yes, we have to keep up shell model. And I don't think too many of us has the courage to throw out the language we are familiar with. So to give you an example, how what I really mean by that is, for example, if you do the calculated double excited state wave function of helium, and you can do the configuration interaction type approach, what you usually call 3s squared single s, you call this double excited state 3s squared single s. If you do the actual CI calculation, you can see there's all kind of configuration mixing. For different state, everybody can do this calculation. You plot, you calculate the coefficient, you diagonalize Hamiltonian, you get all those coefficients out. So instead of talking about you have 3s squared, you have to say I have 72% of 3s squared plus 61% of 3p squared and so on. And that string can be as long as you want, depending on how big the basis that you have. So of course, there's no way for us to visualize or get a picture of what those wave functions are. And of course, it's very difficult to see those wave functions because that is a 6-dimensional beast, and we cannot easily see it. So the key point is, why you want to see it, you have to see by doing the proper, viewpoint. And the 6-dimensional wave function, of course, is very difficult to show it. However, if you choose the right way to see it, you see something interesting, and those wave functions I showed you earlier, they all look the same. And that's where the picture comes in. You have to look at the underlying important patterns. And instead of looking at all those numbers like this, you don't have to remember the number in the sign. You begin to get the mental pictures and then try to understand what the picture means. So of course, this is the basis of all the classification scheme. And of course, this is not the title of this session, but since the Rydberg atom is not quite the area of my work, but I just want to emphasize, because of the problem involving double excited state, and from there Ugo introduced this hyperspherical coordinate, and that was done in the 1960s and 70s. When you start doing hyperspherical coordinate in 1970s, nobody paid attention to you. What's that? But you can see in the last 2-3 decades, this hyperspherical approach has been generalized to many different areas. For the atomic system and for the 3-body system where about the particle mass are about the same. We have heard a number of talks, talking about the 3-body bosons, fermions. In fact, you can also use this hyperspherical approach to do partition scattering on atoms, chemical reactions, in nuclear physics, halos, and all based on hyperspherical approach. In doing ion-atom collision, for example, there are familiar problem beyond the so-called molecular approach, and then this hyperspherical approach now has been generalized to do ion-atom collision as well. So if you think about the history of this guy, it all starts with this person. Because there's some experimental evidence, kind of force us to give up, the language we normally use, and from there you build up new framework, and from there you go to a new area. Okay, so that's my brief remark. The session this afternoon has to do with Rydberg state in matter and antimatter. Usually you create Rydberg state from the ground state, and the Rydberg state is just some inconvenience you have to go through before you reach ionization. But there's of course a lot of interest involving Rydberg state. So there'll be 2 talks on the Rydberg state. You start from the ground state, one given by Thomas Kierman, and on the experiment, and Francis Robichaud will talk about the theory. There is another talk be given by Jerry Gabriel. He will be talking about antihydrogen. In this case, the Rydberg atom will be formed through the recombination process. Of course, when you have recombination, Rydberg states always are produced. These 2 talks tie a little bit closer, so what we're going to do is we'll change the program slightly. Gabriel will give the first talk, and he will tell us whether he has seen antihydrogen. He just came back last night from CERN, so you have the most up-to-date information.